Bonjour à tous. Good morning. So effectively, I'm Stéphane Tanguy. I'm working for EDF Labs. So I'm the CIO, so I'm in IT operation. And I'm also a CTO leading a research program on IT technology. So I'm also a foot in operation and a foot in the future. So what I wanted to talk about this morning maybe is give us our experience in quantum computing. Obviously, as a utility, electrical utility, we're not in the race of the best qubit, but we are definitely interested in developing a quantum algorithm for very interesting use cases of the grid. So our specificity is that we decided basically to start pretty early, back in 2018. So I thought it would be interesting to convey some of the learning that we've learned through this journey from classical to quantum. So before that, just for the non-French, every French know what is EDF, but for the non-French, EDF, basically, we are a large utility. We're pretty proud to have decarbonated mix. Our electricity, the electrons are producing are 90% carbon-free, and our mix derive about 3/4 from nuclear, 10% roughly, depending on the year, from hydro, and a growing part of renewable. So definitely, nuclear is a key legacy for us, and we're investing obviously in new nuclear with the support of France 2030, as was mentioned before. The other particularity is that we do invest a lot in R&D. Probably we're putting this budget of €500 million, and that's probably the highest budget that is put in research from a utility. We have close to 2,000 researchers, mostly in France, but in other parts of the world, China, US, and Europe as well. In terms of investment, there's kind of 2/3 of what we're doing that is in direct support to our businesses, and we developed research for the complete set of business from generation, electricity distribution, and energy management, and reselling that. There's another third of this budget that is basically dedicated to prepare the future of the grid, and quantum is definitely part of this, I would say, pocket of investment. So that's where we decide, as an R&D guy, to invest in the technology that we think are the most valuable for designing the future of the grid. So in order to understand why we've been investing in quantum, you have to understand one of the key pillars that we've been investing for the last 20, 30 years. That's essentially simulation and HPC. The reason for that is we need basically to simulate a lot of the physical phenomena to ensure the safety and the performance of our means of production. As you can imagine, we've got the highest density of nuclear power in one territory, so that puts a certain piece of responsibility on us. The other important thing is that, as you may know, the electricity grids, you need to balance production and consumption at every moment. So we do a lot of optimization. We continue to invest in that. There's more than 100 researchers working on that. Obviously, we're using AI extensively, and that runs on our HPC. So on the whole, for the last 20 years, we've been developing more than 500 codes to basically run and to be able to model all those different constraints. So I think you can see me coming is that if we want to remain state-of-the-art, we need basically to understand what will be the impact of quantum of those set of portfolios of codes, and what will be the impact of quantum. So that's where basically we've been looking at where quantum could play a significant play across the grid. And as you can see, it basically play across the complete value chain of the grid, from power generation, where we'll be interested in understanding how material will be aging. We'll be interested into if we can run partial differential equation. That's basically the core of the solvers and of the codes that we have. We want, I mentioned it, understand what can it bring to optimization. Another very interesting use cases was the smart charging. So, and something that could be really interesting in the future for the grid is when we'll have millions of electric vehicles in the field that basically are batteries and wheel. Those batteries won't be used 100% of the time. You will see probably less than 10%. How can we use basically that potential of energy basically to serve the grid when it's necessary, giving back some of the value to the car owner? So very rich set of use cases. Give me a moment, please. So a pretty rich set of use cases that we've been developing in the past. And in order to do that, basically, the key thing was to build a skill set. And when we started back in 2018, a quantum computer scientist or a quantum software developer that basically didn't exist. So we had basically to train them and skill our people. So the way we did that essentially is by hiring a PhD, with top mathematical skill, and basically have a kind of cross-fertilization between some of the top senior researchers that are very deep on their domain and know exactly what is the state of the art in classical computing. So there's a kind of a cross-fertilization between those guys, very knowledgeable state of the art in classical, and as though young guy bringing those, understanding progressively the zoology of quantum algorithm. So, and definitely our approach was to publish everything we do, so that's an open science approach. So that's for the internal piece. Very important as well as the development of an internal team is basically leveraging and contributing to the ecosystem. Everything that we do, we couldn't have done it without all the time of logo that you can see here, and I didn't put them all, but you'll see that the French startup that were mentioned before, the large IT companies, academics, and the support of European program and regional program as well. So giving you some little zoom on use cases that will be developed tomorrow by Joseph, I think is in the room. But just to give you an example on material, here we wanted basically to understand the aging and the radiation of nuclear vessel. So nuclear vessel is basically, vessel is a cube in French. It's basically the only thing when you want to upgrade a nuclear plant, that's the only thing you can't change. You can change probably everything else, but that you can't change. So if you want to expand the life of a nuclear plant, basically you rely on the lifespan of the vessel. So understanding basically specifically the stainless steel that we're using in the internals of the vessels will be aging. That's the key things, and that's the key scientific challenge that basically our safety authority wants really to understand. So far in classical computing, we were basically using ab initio calculation with a methodology that's called DFT, density functional theory, and which has some theoretical limitation, and specifically you want to understand the paramagnetism, which is exactly the case of the steel that we're using. It's also very, it takes a lot of time from classical computing time. So we've been approaching quantum computing, and we've been developing our own algorithm, methodology with slate spin method. And we're about basically to, we've been emulating this so far, and we're about to run those algorithms on a proof of concept with the production Pascal machine, and we have great hope to be able basically to move beyond the emulation that we've been able so far. So I think that's really interesting, and we hope to be able in the next year to come up with a 3D system and to be able to model molecules that will be more complex and full representation of what is exactly on the field. Another example is the solving of the partial differential equation, and one of the key message here is that we've been trying the kind of off-the-shelf algorithm that you might know, HHL, VQE, and that basically didn't work. So we had basically to do the math in order to adapt those algorithms, hybridize those, in order to be able to leverage quantum to address this type of mathematical equations. And we decided basically to focus on some of the key criteria that are interesting for the field, not trying to model everything that we were, as we used to do it in a classical computing with a complete mesh of, for example, a dam, but to focus on, for example, the rupture criterions. What will basically lead to a crack in a possible concrete structure? And so we've been effectively formulating the problem, we've been running it in emulation, and we're about basically to also be able to run this on a photonic computer from Quandela and to see effectively how we can extract the value from these equations. So what is interesting is that when you look at the state of the art of simulation, and when you want basically to represent through a mesh of your structure, well, with only 30 good qubits, you'll be able basically to have the degrees of freedom that we currently have in classical computing. So that's basically two sets of examples. One other things I wanted to mention as well, another angle which is not only I would say the performance angle and trying to address some very complicated, difficult problem that we have difficulty to model in classical computing, but also the energy aspect. Obviously, being from EDF, we're interested with that, but the point here is to say that if we look at the consumption of a supra-qubit today, and we just say, what would it take if we scale to 100 and 1,000? Well, the energy consumption could be quite huge if we don't do anything, if we don't optimize that. So the objective of this project is basically to while we're developing the qubits and while we're scaling up our quantum machine to understand, to make sure that we get an energy advantage from quantum. And in order to do that, as you can see, we have some of the key partners. Obviously, as EDF, we're bringing the application, the use cases, and the knowledge of exactly what does it take in terms of a kilowatt hour to solve one problem in classical. Compare that to what does it take in basically running some qubits along the full stack. Okay, so in terms of roadmap, the last 5 years we've been spending in terms developing, understanding the quantum algorithm zoology, I would say. The target calculation was essentially emulators. Now we're moving into phase 2. We do have a set of quantum software portfolio, and we're moving to those onto real machine, the real machine with kind of 100 of qubits, and the noise that we have today, and see effectively how does that work. The next phase for us, obviously, will be, if that the phase 2 is conclusive, basically to move and adapt the production code that we use on a day-to-day basis that serve basically to run the grid today, to be able basically to adapt our code. And some of you guys might know Quadracer, which is briefly famous in mechanical, and turning in a quantum Quadracer version. So just to conclude, a couple of takeaway messages. I think if we look back 5 years ago, I think we started early, we made a significant investment in that, and we're kind of glad we made an investment. The reason being is that effectively, as I mentioned, there's very few off-the-shelf algorithms that work for our cases. So the investment that we made in building the skill set, I think, was worth it. And that gives us basically a way to see exactly where are we in the advance of the technology. And the other key message is essentially that collaboration and partnership is absolutely key. We've been working within the ecosystem. We just think we are part of this ecosystem. And I think that within the coming years, we need to preserve that spirit of collaboration. Let's not try too much in monetizing too early, because there are still some research to do, and there are still some technology logs, and that will be solved collectively, essentially. Thank you.
Question? We do have just a minute or two for a question, and we have one that's come through the app. Stefan, this is related to the skills of the workforce. You mentioned 1 or 2 points about the PhDs that now work at EDF, but more generally across the workforce in quantum, do you see a lack of skills, and how much more work needs to be done at different levels of education?
Well, yeah, I think there are, as I mentioned, for us, quantum is a scientific tool. So that's the reason for us. There's a high stake from an R&D perspective, and given the effort we put in simulation and running the day. So I think the level of training, the level of knowledge you want to bring to your workforce for a company, that depends on the stake that you see in quantum. I mean, what does it represent for your company? Is it effectively something where you believe that it's going to give you a competitive edge and competitive advantage? We think this is the case for us, so that's why we started early, and that's why effectively we have trained those, we have taken those PhD and making sure able. We started also training our IT organization. At this stage is essentially making sure that they understand what's coming, they understand the hardware, the infrastructure, key question that still are to solve, because obviously operating an HPC, operating a quantum machine, that's quite different. And there are a number of questions that they need to think about, especially in our case when basically we own our own data center. So that means that when you want to plan the next one, you need to start thinking quantum effectively.